Okay, so well, let's start because I see that there is no nobody else coming. Well, first of all, sorry for the sudden announcement. Okay, so the idea was to have it announced in a proper way, but we have to change something in the web for that to happen. So it's in process. Okay, so the changes. After that, it's a pleasure to introduce David Soriano. That I mean, David and me met a long ago. I think it was in Portugal, but in Lisbon, or in Porto, I don't know, in a conference. Oh, yeah. And he did the PhD in Zaragoza, I think with Jesus Gomez Gardeñez and Alex Arenas. And later he was a postdoc in the Gulbenkian Foundation in Lisbon for a few years, and now he's back, but not to Zaragoza, but to Tarragona, so to the other the other alternative place. And he's working in coevolution, I mean propagation of diseases and coevolution of viruses. No? So well, the floor is yours, David.
Okay, Jose, so thank you so much for the kind introduction. I mean, and thank you all for coming here. Actually, I was telling some of you that I was feeling a bit ashamed because I've been working for 8 years in complex systems and I have never been here. So now I'm solving this issue, right? And today I would like to tell you about a recent research line we have started in the lab in Tarragona, in which, as Jose was saying, we are trying to couple evolution and epidemics, okay? But before starting with this topic, I just want to tell you how I got there, how I started working on this very exciting topic for me. I mean, as any network epidemiologist here in the room, I started like working on how human behavior shape the propagation of diseases, right? At the very beginning of my PhD, I was just focused on this interesting question that basically tried to address how the way in which we move across city shape the impact of outbreaks on urban environments, okay? And then I think that we are in the room, we are all aware of this fact, COVID-19 hit us. And obviously I had to change from the theoretical domain to the more applied modeling in which we were trying to propose these mathematical frameworks to some sort of forecast the evolution of the COVID-19 curves. And more importantly, we're trying to provide the authorities with frameworks in order to design policies that were intended to mitigate the impact of this very first severe epidemic wave, okay? And for instance, here you have one example of the outcome of our model in which we were able to predict quite well the decrease of the pandemic after the policies in the first epidemic wave. But I mean, looking retrospectively, although as a community this work was very important and all the modelers involved in this endeavor were contributing a lot to the management of the pandemic, I realized that being able to tame the first epidemic wave and being able to understand what was going on in the first wave is just understanding a very little piece of the entire story that an epidemic represents, right? So here, for instance, you have data about the number of cases of COVID-19 throughout time, and you can observe a very rich dynamical behavior, right? So we have this very first epidemic wave, but then we have a consecution of waves that are occurring after a given time until we end up in a sort of endemic scenario, okay? Yeah, that is data for spring, yeah. So this kind of transition from the well-characterized pandemic scenario to the long-term establishment of diseases obviously is not only characteristic for COVID-19, but also has occurred for many other diseases. So for instance, every single year we are witnessing this kind of influenza seasons in which there is a periodic behavior of the epidemic curves, okay? And we have this kind of oscillatory patterns that typically are repeating one another in a period of 1 year. And for instance, apart from the influenza and the COVID, we also have other kind of diseases, such as vector-borne diseases, that might be endemic in other areas. And for instance, this is the curves that you can observe in a Colombian region for the dengue virus, okay? So with this, I just want to say that focusing ourselves on a first epidemic wave maybe make us lose or prevent us from being able to capture the entire richness that this dynamical behavior represents. And not only that, what is important is, if you think across time, the features of the viruses that are circulating nowadays might be completely different from the features of the virus that originated the disease at the first instance, okay? And we're all witness of this kind of evolutionary processes during COVID-19 pandemic, right? Because we saw that there was a compatibility between the time scales across which the virus was evolving and the time scales across which the virus was unfolding across our populations, okay? And because of this compatibility, we observed that, from the wild type variant, there were other variants emerging, such as Delta, Alpha, or Omicron, okay? And obviously, this is not a COVID-19 work. This is also typical for other viruses. And if you analyze influenza A virus, what you can realize is that the features of the viruses that causing every single season all over the years are completely different from the former variants that were circulating in the population, okay? And this kind of compatibility of evolution and epidemics also occurred at some point for this dengue virus, because at some point the initial dengue virus was split into 4 lineages that nowadays are circulating in a stable way in the population. Okay, so this clearly identify a gap in the literature and in our understanding of epidemics, because these are 3 examples in which evolutionary processes are compatible with the spread of diseases. Okay, and if we want to characterize entirely the epidemic causes by these viruses, we should couple evolution and epidemics under a single framework. And basically, this requires a shift from the usual models we are using in network epidemiology to eco-evolutionary frameworks that take into account the apparition of mutation in the populations, and also how the ecology of the virus determines the emergence and the prevalence of some variants over the others that are circulating in the population. Okay? So with this new research line, we are trying to set light into these questions, right? So for instance, how the mutations that occur during the replication of the virus inside the host affect the epidemic curves that we are measuring at the population, but also the other way around, that has not been that explored in the literature. How the actions that we are implementing at the population level are determining the way in which the virus is evolving in an effective way. How these actions are determining the way in which different variants might emerge and prevail in the population. Okay, so this is kind of the broad scope of this new research line we are working with in the lab. We are open to collaboration, by the way, so if you're interested in the topic, just reach out to us, okay? But in this talk, I want to narrow down the scope a little bit of our topic, and we're going to be focused on trying to answer this question. So how does evolution determine term behavior of epidemic trajectories? In other words, how does evolution shapes the transition from the pandemic scenario, this clearly single wave behavior, to the long-term establishment and circulation of diseases in populations, okay? And to answer this question, as I'm a physicist, we want to follow we want to propose the most minimal eco-evolutionary framework that we need in order to account for this evolution of the virus. So to start with, we are going to propose a compartmental model. And basically, the compartmental model is a way of summarizing all the nuances, all the complicated course of the disease inside host in a few but informative compartments, okay? So here, for instance, the most paradigmatic model is the SIR, in which we assume that the course of the disease inside a host is represented by 3 compartments. You can be susceptible, meaning that you have not been infected before, okay? And you are completely prone to become infected if you are contacting an infected individual. You can be infected, meaning that you have the pathogen and you are able to transmit the pathogen to others. And you can develop some immunity at some point and become recovered, okay? Meaning that if you are facing the same pathogen in the future, you are not going to be infected again, okay? So apart from defining the compartments of the model that summarize all these complex biological processes that are occurring inside us, we should also define the flows of the model, okay? And this SIR model is very simple. We have the contagion flow, meaning that a susceptible individual can become infected if he or she is interacting with another infected individual, and there is this rate lambda at which this infection processes occur. And you also have the recovery rate, that in this case is spontaneous, okay? After some point, you develop some immune response. This immune response is able to fight the viral load that you have inside, it clears the pathogen, and you become recovered. So another important quantity for this talk is going to be the effective reproduction number, okay? And this effective reproduction number in epidemiology is just basically what is the size of your offspring. So how many infected individuals you are generating as an infected individual, okay? So if you think about this, if this number is above 1, you have a multiplicative process and the cascade of infections is growing over time. That means that you are going to generate an outbreak, okay? If it falls below 1, that means that if you introduce an infected individual, it is very likely that the disease ends up vanishing, okay? And you don't have any outbreak. So for this very simple analysis, if we want to understand the sustained circulation of an outbreak in the population, one requirement that we have to fulfill is that this effective reproduction number is greater than 1, okay? So now we wonder ourselves whether this SIR model can meet this requirement, okay? And the answer is no. Because if you simulate the typical epidemic course of this model, you can observe how you can generate a single outbreak. But in the end, you end up with infected individuals, okay? And if you take a look at the reproduction number, although at the very beginning you were infectious, you were generating these outbreaks, there is a point in which you cross this line and you are below the desired threshold for keeping circulating the population, okay? And this occurs, and it's very simple to understand, just from the flows of this SIR model. Because if you take a look at these flows, you realize that there is a sink in the dynamics. So the recovery compartment is a sink. So everyone that is entering into this compartment remains dead forever, okay? And that means that in the end, you are going to have a population that is split between susceptible and recovered, and without infected individuals, okay? So with this very simple qualitative analysis, it is clear that this SIR model has to be complicated in some way in order to capture this long-term establishment of diseases. And actually, what we need is to kind of replenish the susceptible population, okay? And we need to replenish this population by the loss of immunity of recovered individuals, okay? Because the disease requires fuel to keep growing. So it requires more and more susceptible population. So what are the typical mechanisms for the loss of immunity? I mean, there has been a mechanism which has been widely explored in the literature, which is the so-called waning immunity. And qualitatively, this is very easy to understand. So imagine that you were recovered at some point, meaning that you develop some antibodies for a given pathogen, okay? But there is enough time during the disease that at some point, your antibodies levels start to decrease over time, and in the end, you behave as a susceptible individual because your internal concentration of antibodies has decreased that much that you behave as if you weren't develop any kind of immune response against this pathogen, okay? So if you want to accommodate this waning immunity mechanism, which is again the one that has been widely studied in the literature, we are not discovering anything new here. What you have to do is just basically introduce a rate from the recovered compartment to the susceptible one, okay? And as you can observe, just with this very simple modification, you have this damp oscillatory behavior that in the end ends up in a steady endemic state, okay? So the SIR model allows you to capture this establishment of diseases. However, for the kind of viruses we are interested in, there is another mechanism that allows you to understand the loss of immunity, okay? And this mechanism is the so-called antigenic escape. So imagine that you were recovered, so you develop an immune response against a circulating pathogen at a given point of the outbreak, okay? But now remember that the viruses we are interested in have comparable evolutionary time scales with the typical time scale of the outbreak. So it might occur that the features of the virus start evolving during the outbreak, such that at a given point in the outbreak later, the features of the circulating virus are completely different for the virus to which you develop immunity. So you still have antibodies. These antibodies have not decreased over time, but you are not able to recognize, to attach to the circulating virus, okay? And this causes that you are behaving as if you were susceptible because you have some defenses, but these defenses are not prepared to recognize the circulating pathogen. And this is what is called antigenic escape. So now the idea is how can I accommodate this antigenic escape in a simple way in my SIR model, okay? And this is difficult, of course, because if you think about this process, this has a lot of biological implications. So in principle, you should be aware of all the biological mechanisms involved in the attachment of antibodies to the antigenic proteins of the virus, and in the neutralization of the pathogen inside you. So, as I'm not that expert in biology, I'm gonna follow kind of our physicist approach. And what I'm gonna assume as a first approach, we'll refine this approach later on, is that all these antigenic properties of the virus are summarized in a position of the virus in a 1D line, okay? So basically my antigenic space now is gonna be a line in which I'm gonna locate every circulating virus in the population, okay? And the distance in the line reflects how different two viruses are, okay? So if I want to accommodate the antigenic escape mechanism within this framework, what I have to assume is that the greater the distance is between your variant as a recovered individual and the variant that is circulating in the population, the more likely you are to contract the disease, okay? And this is what we are gonna introduce in this new eco-evolutionary framework. Basically, we are gonna assume that for recovered population, the reinfection probability increase with this antigenic distance, okay? So now we have all the ingredients in order to propose our framework. So in this framework, we are gonna have that each virus is gonna be characterized by two features, okay? One feature is the infectiousness of the virus, so how transmissible the virus is across different hosts. And the other feature is related to the antigenic position that we have been discussing before. Okay? Now, in terms of the compartments, we are going to introduce the typical SIR model. And of course, we are accounting for the contagion flow, meaning that if you interact with an individual that has a given virus, you might become infected and you inherit the strain by which this individual was infected. Okay? And you are also accounting for the recovery, meaning that at some point you might develop immune response and you might transition into the recovered compartment. But as a recovered individual, you keep memory of the last infection to which you develop immunity. Okay? So now, if we want to accommodate this antigenic escape, what we have to do is to introduce this reinfection flow. Okay? And have a look at this flow because unlike the other two ones, this flow depends not only on the circulating variant, okay, which is the J index with respect to the infected individual, but also depends on the focal agent that is going to be infected, okay, because it should account for the antigenic distance between the last variant to which you develop immunity and the position of the virus that is circulating in the population, okay. So among all the possible functional forms that one can propose in the literature, I chose this one, okay? Because this one fulfills what I want for this function. Actually, if you consider that the antigenic position of the recovered individual and the infected individual are the same, you can easily check how this rate of contagion is 0. And this makes sense, right? You cannot contract again the variant to which you develop immunity. And if you assume that this goes to infinity, what you eventually get is that this rate is equal to lambda j. Okay? And this makes sense because if the features of the circulating variant are that so different to the ones that you develop immunity, basically you are behaving as a susceptible individual. So nothing makes you different from an individual that didn't face the pathogen before, in principle. Okay? So now, this is for the compartmental model. Now, on top of this, I have to include the evolution, right? Because we are saying that there is some compatibility between evolutionary timescales and epidemical processes. So how do I model evolution? Again, most simple hypothesis I can make, could be refined, and for sure we are making a lot of biological mistakes, okay? But in principle, what we are assuming is that the recovered individual, as I was saying before, keeps memory of the last infection to which he or she developed immunity, okay? But for an infected individual, if you are infected at time t, okay, let's assume that we have a discrete time dynamics, at time t+1, you are going to update the features of your variant, okay? Because the strain starts replicating inside you, there might be errors during the replication, and this might affect the features of the virus. And to introduce these modifications, we are going to assume that the antigenic position is just updated, and we are going to draw the updates from a Gaussian distribution. Okay, so in effective terms, we are introducing a kind of Brownian motion inside each infected host. Okay, and the variance of this Brownian motion is this Tx parameter. That is going to tell us how quickly the virus is going to evolve within the host. Okay, so basically that's all. This is all our framework, and this is the way in which we are introducing this antigenic escape in an eco-evolutionary framework. Okay, and now the main research question is how this new parameter affect the typical curves that we know for the SIR model. Okay, and in order to set like a baseline scenario, what we are going to do is just to assume this parameter is equal to 0. Okay? If this parameter is equal to 0, that means that the virus is not evolving, right? And we should expect to recover what we saw for the SIR dynamics. And indeed, this is what we get. So here you have the evolution of the fraction of population in the infected state as a function of time. So the dashed lines here are going to be those realizations that eventually become extinct in the population. Okay? And as you can observe here, for all the realizations, I'm seeing this extinction of the outbreaks. So I have the typical SIR model. So now let's put a very high value of this Tx parameter, a very high evolution speed. Okay? So what you can observe here is that we are retrieving some sort of an SIR-like dynamics because we have this very first prominent wave that is followed by multiple waves, and in the end you have this establishment of the disease. Okay? So now the question is that how this long-term establishment is achieved in this framework. Okay? And to answer that, I think that a movie is very illustrative. What we are going to do is to track the distribution of strains across this antigenic space, okay, across this line over time. So obviously at the very beginning, we only have a single wild type variant, okay? So that means that this distribution is a delta, is a direct delta, okay, around this x equal to 0. If I start to run in the outbreak, you can observe some crazy things occurring here. But in the end, when you arrive to some points that are comparable to the ones shown here, what you can observe is that you are building a coherent package of variants, a coherent wave that is traveling across this 1D space, across this line, okay? And what is going on? Basically that this coherent wave, this coherent set of strains, harbors enough viral diversity in order to reassure the reinfections of individuals that are at opposite edges of this distribution, okay? And that's why you keep fueling the disease and you keep accumulating contagion events, okay? Yeah.
Why is it only moving in one direction?
Yeah, that's a good question. So the reason for which this is moving in one direction, is because of this heaviside function here. So why you should account for this, you should introduce this heaviside function. If you are not introducing this heaviside function, imagine that you have a distribution, okay? Well, I can do it with the hands because otherwise I guess they cannot see. So if you have this individual can become reinfected by this one, okay? I can get this disease, but afterwards that one could get this one again. So that means that in 2 steps, you will be able to lose all your immune memory. And this is not realistic, right? So how you prevent that? This is called mirror effect in this kind of dynamics. And the way of preventing that is forcing that you can only get some disease whose antigenic position is greater than the ones for which you have developed immunity before, okay? And this is the reason for which you are introducing this here, and this is the reason for which it is moving across this direction. Otherwise, it will be just a flattening of the curve, and in the end, you will end up with a uniform distribution across this 1D space. And this is not realistic because there will be continuous reinfection because of the Markovian nature of the rules that you are introducing here. Did I answer the question? Okay.
Basically, you have memory
Yeah.
of all the infection.
Yeah, you are introducing this assumption in an effective way by the heaviside function. Yeah, that's true. Okay. So, okay, what happens if we set this dx parameter to intermediate values? What we have is a mixed dynamics, right? We have that some diseases are able to prevail and avoid the absorbing state, and they are able to become established in the population, whereas others are becoming extinct, okay? So obviously, in light of this, we're interested in kind of characterizing what are the features that makes you more capable or more likely to prevail in the population or to become extinct. And to do so, we ran a bunch of simulations. I think that there were like 1,000 simulations, okay, for our systems. And we check how many of them become endemic as a function of how infectious you were at the very beginning of the outbreak and how quickly you evolve, okay? So this is the x-axis, the infectiousness, and the evolution is the color code. So from this figure, you can observe a couple of things. If you set the evolution, sorry, the speed of evolution. Hola, hola. Can you hear me from home?
Yes, we can.
Okay, thank you, Violeta. So, okay. So again, for each speed of evolution, what you can observe is that there seems to be a critical value of the infectiousness below which you cannot persist in the population, and above which you are able to, at least for some realizations, to persist in the population, okay? And this critical value depends on how quickly you can evolve your antigenic features. Also, if you analyze the effect of increasing the speed of evolution, you have this result by which if you evolve more quickly, you are more likely to persist in the population, okay? So summarizing from this figure, it seems that the more infectious you are, the more likely you are to become endemic, and the more quickly you evolve, the same, the more likely you are to prevail. I mean, this makes sense, right? I mean, why did you come here all the way from Tarragona to Mallorca just to tell us this thing, right? Luckily for me, I have still 20 minutes of talk, so maybe I will surprise you with other results, right? And the thing is that with this analysis, we are missing one fact, and one very important fact. So if we just focus on the evolution of antigenic features, what we are assuming is that this antigenic escape is the major driver of evolution of viruses, and is the major mechanism by which we are selecting one variant over the other, okay? And this is true, and this might be true at very late stages of the outbreak, when the population has built some sort of immunity, when you have this immune pressure, right? But at very early stage of the outbreak, this is not true, because basically you don't have recovery individuals. There is no immune pressure, okay? But still, in some outbreaks, such as the COVID-19 pandemic, we saw how some variants were able to emerge and to displace others that were propagating in the population. So for instance, this alpha and delta variant, they were able to prevail in the population because they have more intrinsic transmissibility. They were more transmissible than the others, okay? And that was the mechanism that allowed them to outcompete the wild type variant. Okay? So if we are restricting ourselves to this region, we are missing this fact. So now we are going to see what happens if we introduce this evolution in transmissibility. Okay? And the way of doing it is very simple. So rather than assuming that we are just changing our antigenic position, let's propose that apart from changing your antigenic features, you can also change your transmissibility. Okay? Very simple. And here these two distributions are not correlated, okay? In principle, they are uncorrelated Gaussian distributions, so we are not introducing any artifact at this point. Okay, so let's see what happens. First, for the temporal dynamics. So here I have set some values that allows me to be completely sure that the disease are gonna become established in the population, and also that they are gonna evolve in some way their transmissibility, okay? And here you have the behavior of the average fraction of infected individuals across time for multiple pathogens that differs in their initial infectiousness, okay? So I have a pathogen which was mildly infectious with an R0 that is 1.25, and then to 2 and to 3, okay? So this is the most, in principle, the most harmful pathogen, the one with R0 equal to 3. So what you can observe here, the first is that we have the typical behavior of a first prominent wave, followed by an epidemic bottleneck, and then in this case, as I'm not putting any restriction to the growth of infectiousness, obviously the virus tends to accumulate mutation that allows the virus to keep growing its infectiousness, okay? And that's why rather than having a sustained value or a fixed value of this endemic prevalence, you have this epidemic growth in the long term, right? So what you can observe here, and for me that was very striking at the very beginning, is that regardless of the initial differences, there seems to be a kind of universal slope of growth of these curves in the long term, right? And these pathogens were really different at the very beginning. So now I just want to understand what's going on here. And to do so, rather than focusing on the infected population, what I did is to represent the time evolution of this infectiousness, okay? And you can observe a couple of things from this figure. The first one is that it seems that the initial differences, this gap, is reduced in the long term, right? So it seems that this virus here has evolved more than that one on top. But apart from that, I want you just to, and maybe you should really observe this curve in detail, because there seem to be two slopes, right? Here, you have an initial slope for this virus that is greater than the one that it follows afterwards. So that means that at the very beginning of the outbreak, there seems to be an accelerated evolution in infectiousness compared to what happened afterwards. Okay, so this is for the infectiousness. Now, let's have a look at the distribution of our strains across this antigenic space. Okay, so what you can observe here is that at the very beginning, the variance of this distribution is not very relevant. It's not evolving at a very high pace, right? Whereas at later stages, we have this huge increase in the diversity of the strains that are propagating in the population. Okay? And again, this makes sense, and this corresponds with what we were describing quite actively before. Because at the very beginning, the way for variants to prevail in the population and to displace others is just to increase their intrinsic transmissibility, right? Because everyone is susceptible. So the way of prevailing above others is just being more infectious. But when the population is immune enough, you don't only, you, apart from being more infectious, you really require to be antigenically different from the other variants that are in the population and that have caused previous outbreaks, okay? So that creates the fact that at this point, you should really make your distribution wide enough in order to harbor the diversity that you require to prevail in the population, right? And then you have this kind of decrease that corresponds to the increase in infectiousness, okay? So, from this figure, another thing that you can also observe is that if you have a virus that is less infectious, you have to create more diversity in this point, okay? So here you have the peaks, and it is clear that the package of strains that are propagated in the population are more diverse if you start with a virus that have lower infectiousness. Okay, so that kind of tells you that there is a trade-off between the antigenic diversity you should create and your intrinsic infectiousness. The less infectious you are, the more diverse antigenically you have to be to persist in the population. Okay, and basically this is the origin of this universal behavior here. Now we can shed light into this universal behavior because I can propose a new definition of the effective reproduction number. Okay, and this new definition does not only account for the typical reproduction number, that is basically the product of your infectiousness, your number of contacts, the fraction of susceptible, and the duration of the period, but also takes into account that you have a new pool of susceptible individuals that are those recovered individuals that are very different from, okay? And in order to account for these differences, we can introduce here just the standard deviation, for instance, of this distribution of values, okay? So if I compute the time evolution of this new quantity, what you can realize is that although initially you have a lot of differences between the circulating variants, okay, there is a point in which the three of them converge to the same value, okay? And this is telling you that in some sense, the intrinsic infectiousness is being compensated by the antigenic diversity that the virus is generating, okay? To give rise to this some sort of universal, and I'm putting quotes because I haven't checked it properly, behavior, okay? So this is from the temporal point of view. Now let's go back to our previous plot in which we're asking ourselves what are the features that are making me more likely to prevail in the population. So if you remember, that was the picture, the very nice picture we had when we were forgetting, when we were neglecting the evolution in infectiousness, okay? So basically, the more infectious you are, the more likely you are to become endemic, and the more quickly you evolve, the more likely you become endemic as well, okay? Very simple. Now let's introduce evolution in infectiousness. And you can realize that a very interesting behavior emerged, right? And this interesting behavior is that there is a non-monotonic behavior of your probability of becoming endemic, okay? Meaning that if you were initially less infectious, okay, maybe you are more likely to prevail in the population, okay? And this for me at the very beginning was very counterintuitive. I was very surprised. I mean, I was excited because it gave me room in order to try to understand what was going on. And I have two ways of proving this. Maybe I should skip the quantitative proof because I don't have time. If you are interested, we can discuss it later. But qualitatively, in this context, we can understand why this happens. Basically, think of a simple SIR model. Okay. Now forget about all we have discussed. And let's put how the epidemic curves in the first epidemic wave look like, okay, as we are decreasing the initial infectiousness. So this is the epidemic curve for R naught equal to 2.5, to 2, 1.5, and 1.2, okay? So as we move from 2 to 1.2, what you can observe is that we have the so-called flattening of the curve, okay? This means that we are reducing the magnitude of the epidemic peak, and obviously this is beneficial for us, okay? Because we are inducing less stress to the system in the worst moment of the outbreak, but we are extending the duration of the outbreak, okay? So we are slowing down this epidemic wave. And in principle, and in all these epidemic models, if you don't take into account evolution, this is completely harmless, right? Okay, I have more time, the outbreak during more time. If I'm capable to cope with this outbreak because I have enough resources, I don't care. But now, as we take into account evolution, there might be a detrimental effect of introducing this extension of the wave. And basically, the detrimental effect is that I'm giving the virus more time in order to evolve to meet the features that make it likely to prevail in the population. Okay? So this is kind of unveiling a trade-off between the beneficial short-term effects of introducing a policy and its potential long-term consequences. Okay? Only this is not, I mean, this is not occurring for every single policy, and it depends a lot on the duration and on how severe the policy is. But there is this potential effect that for me is interesting, and that is completely linked to the fact that you have this compatibility between the time scales of evolution and the time scales of the epidemic. Okay? So that was the analytical explanation. I'm gonna skip it because otherwise I don't have time to go to the last point of the talk, okay? So far, I was telling you that I was missing a very important feature, that is the fact that it can evolve infectiousness. But with my setup, that is basically summarizing all the antigenic features of the virus in the position of this virus in a 1D space, I'm also overlooking the fact that I might have access to a lot of genomic surveillance data. So I might, as a network scientist, I might have a more suitable representation of this antigenic space than just this abstraction to a 1D line, to a line, okay? So more specifically, nowadays there is more and more genomic surveillance data available for us. You can, there is some data bank as well, and you can download the entire sequences of the proteins that are involved in the attachment of antibodies to the virus capsid. Okay? So basically, the idea is that once I have the sequence of amino acids that are composing this protein, I can create a network. Okay? And in this network, each node is, as I was telling you, a sequence of amino acids, and there is a link between two nodes, between two sequences, if they differ in a single point mutation. Okay, if there is one amino acid that change from one sequence to the other. Okay, so this way I can create this network. So now I no longer have a 2D continuous space representing the strains that are circulating in my system, but instead I have a network that is containing, that is capturing all the possible strains that might circulate across an outbreak. Okay, so I have to change my framework. And the idea is, rather than relying on this kind of continuous kernel of reinfections, I want to propose a system of ODEs that takes into account or that incorporates the antigenic escape mechanism into the epidemic modeling. Okay, so these are the set of equations I'm proposing. So this is the evolution. This is basically an SIS model in which, as a novelty, rather than introducing an additional compartment, that is the recover compartment in which you keep those that have the low immunity, we are introducing the immunity in the recovery rate. Okay, and we are assuming that if you faced an outbreak or a pathogen at a given point of an epidemic, that means that the pathogen can stimulate your immune response, okay, and you can generate antibodies that might clear the pathogen earlier than if you were a susceptible individual. Okay, so in an effective way, if you clear the pathogen in a shorter time, that means that your infectious window is shorter. Okay, and that you have increased your recovery rate. Okay, so this is the way in which, in order not to account for more equations, we are just introducing all this generation of immunity through the time dependence of this recovery rate. Okay. So how are these equations? Very easy. You have that the time dependence of the fraction of infected population of strain I is the typical contagion term, the recovery term, okay? And here you have the evolution term, okay? That is just a random, in this case, we assume that you have a random, that mutations are causing a random walk across the network of mutations, okay? So this is the Laplacian here. In terms of the recovery rate, you have that you are going to increase the recovery rate, okay, at a rate that is proportional to the fraction of population that is infected by this specific strain. Okay, so the more people infected to some strain, the greater the collective response to this strain is going to be in the future. Okay, so this is a mean field assumption that, of course, has some biological shortcomings, but allows you to simplify a lot the mathematical treatment of the model. And then, apart from assuming that you are building immune response against a given variant, you have to assume that if you contract this variant, you might also be immune against the neighboring nodes in the network. Okay, and obviously this immunity is going to decrease as you are farther away in the network. Okay, and this is the term that we are introducing here. Okay, you can gain immunity for variant I if you contract a disease J that is close in the network. Okay. And here you have a characteristic length of this antigenic immunity. Okay, so this is the new framework. Another idea is, okay, now I have this framework, I can see where is the effect of the complex topologies or architectures that I have in real networks in the epidemic trajectories I'm observing.
The memory of the previous contagion. You take into account what you are contagion now, you are immune also to something to be similar to that, but you forget you have been infected before.
No, because you don't have a negative term here. So you might have that option if you have a loss term here. Yeah, you are accumulating. You are just increasing the recovery rate of all the strains you have contracted throughout the outbreak. Yeah. So we're also trying to introduce a memory loss term here, And the problem is that the trajectories were chaotic. I mean, because you were able to come back to the net. I mean, that wasn't very realistic, as we'll see right now. Okay. So now the idea as a baseline, again, as a baseline scenario, what we want to do is just to recover what we knew in the low dimensional antigenic space, right? And to do so, what we assume as a toy model is that we have a lattice. Okay? And here you can observe how our equations generate this behavior in which we have a damp oscillatory behavior towards an endemic state with a steady prevalence. Okay, so that's okay. But now, is this representation realistic of the networks, of the real networks we were seeing before? The answer is no, because if we characterize the structure of these networks, the first thing we can realize is that they have some sort of scale-free behavior. Okay, meaning that there are hubs in the antigenic space, and their connectivity is way more different from the connectivity of a typical node in the network. Okay, and obviously you cannot capture this path with a regular graph like the lattice. Apart from that, if you compare this network here with some networks that are generating with a null model, what you can see is that these networks have longer path lengths. Okay, and this makes sense because there is some sort of fingerprint of the low dimensional assumption that people were making. Okay, so you can see here that obviously this network is not that small as the ones we are used to, okay, because there is some sort of geometrical dimension that the length of the shortest path. And apart from this, you can observe how these networks are, on average, more disassortative than the ones that you will obtain in a null model, and you have more modularity. Okay? So because of these three features, we thought, okay, let's propose a toy model that can replicate these three features. And our toy model was just assuming that you have a collection of hubs that are linked through some key bridges. Okay? So now, what is the kind of dynamics you are observing if you introduce this architecture? So what you can see here is that the dynamical behavior of the curves is completely different, right? And rather than having this convergence towards this state, the complex structure of this antigenic space is causing this seasonal behavior. Okay, and we really like this result because most of the times when you want to introduce seasonality in this kind of epidemic models, in the end you end up putting or like inserting a seasonal dependency of the infectiousness, right? And this is justified for some diseases. For instance, vector-borne diseases, you really need to account for the seasonal dependence of climate. But in other diseases, such as influenza, maybe you don't need that argument. Maybe you just need to account for the fact that you might lose immunity because the virus is mutating. And what is causing this seasonal behavior is the appearance of dominant variants over time with a period. Okay? And actually, if you play around with these modules and you are modifying the number of leaves that is in this kind of in these individual modules, what you have is rather than having this regular pattern, you have irregular seasons. Okay. So just to finish, we wanted to test this in a real outbreak. So we took the empirical data of the H3N2 virus that was collected from 2010 to 2018. So here you have the time at which each variant was first sampled in the data. Okay, and what we did is to put our seed in the first variant that was sampled and then simulate an outbreak with these rules. Okay, so here you have the picture that we obtained, and as you can observe here. And this is like the quantitative characterization of the time at which the sample appeared in the simulations and the time at which the sample appeared in data. There is a good correlation between our model and reality. And that means that antigenic evolution for this influenza virus is just providing us with a very good picture about how the epidemic is unfolding. So we don't need to account for any external source such as time dependence fluctuations of the weather conditions. So just to finish, that was our initial question, and I hope I have convinced you about the fact that there is a mechanism that has not been that explored by our community, that is called antigenic escape, and that allow us to justify the long-term resistance of viruses, that there might be a potential trade-off between the short-term and the long-term consequences of acting on epidemic outbreaks, and that seasonality is something that might emerge from the interplay between the immune pressure, evolution, and epidemics. And this is not something that should be ad hoc. So the most important message of this talk is this one. We are organizing, as you are all aware, maybe because we are spamming a little bit, we are organizing a conference in Zaragoza. Okay, we have a very good lineup of speakers that merge experimental biologists, anthropologists, and also our usual suspects. So I really encourage you to come and to join us in Zaragoza. And then another important message for sure are the acknowledgements. So I would like to thank the support and all the discussions and the collaboration with my usual colleagues Jesus and Alex, and also Santiago, that was the PhD student that was performing all the simulations and all the characterization of the last study, okay, of the relevance of the network. Here you have the two works that I have talked about. The first one is the one in which I have this non-monotonic dependence of the endemicity, and the last one that is in the archive right now is in press, and that it will be published, I guess, that in some weeks. So some contact data, and thank you so much for your attention.
Thanks. Yeah, questions?
So thank you very much, David. I enjoyed the talk. So I have two questions plus one observation. So the first question is, what exactly is the difference between your model and a reaction diffusion model for the epidemics, in which the diffusive part is your compartmental part and the reaction is the transformation of the immunity of people that you took from the virus point of view, but what is happening at the end of the day is also changing the immunity of the people. So there are many reaction diffusion models for that. Possibly related to this is that in the original data that you show, for instance, for Spain, there were some peaks in more advanced time. Let's say that for T2 larger than T1, the height of the peak is bigger for T2 than for T1. However, all your simulations start from a big peak, and then the further seasonal peaks are much smaller. Have you thought what is the cause of that and how can be solved? And the observation is that in the reaction diffusion models, you can incorporate very easily the memory of the system by changing the time, the temporal standard derivative by fractional derivative, and there is no chaotic problems about that. Thank you very much.
Okay, so thank you for your questions, Ernesto. So for the first one, for the reaction diffusion process, I agree. This can be mapped into a reaction diffusion process, but the way in which people have done it is the other way around. Actually, reaction is linked with the contagion processes that are occurring at a given position, whereas diffusion is assumed to be the diffusion of the virus across this antigenic space. So the mutations that are allowing you to visit the different coordinates of this antigenic space that you are proposing. And in the literature, there are many works that are framing this into a reaction diffusion process, and they are finding the typical predictions of the traveling wave behavior with the FKKP and all these things. But the difference of the first work with this is that they were neglecting the evolution in infectiousness. So until the part in which I was explaining the evolution of antigenic features, this has been done in the literature. But they were not taking into account the first part, at which you can also change your transmissibility. And that was the part that was giving me this rich behavior of this non-monotonic effect. So that was the main novelty of the work. Then for the second question, in which you are asking me about the height of the first peak, so what happened is that, obviously, in COVID-19 pandemic, we acted on the peak. So we control the peak. So it's not like the first peak of the COVID-19 pandemic is not the free propagation of the outbreak. It's the result of lowering down the infectiousness over a long period in which these control policies, these population lockdowns, curfews, travel bans, and so on, were implemented. Okay, so
But it's not possible that, for instance, for flu, the virus developed much more infectability, and the second wave is much bigger than the first one, even without any intervention.
there might be a possibility. Yeah, I think so.
Yeah, in the case of COVID, the R0 measuring constrained conditions in the last versions of the COVID are way much higher, no, than the original one, the wild type. So essentially, the virus is becoming more and more effective as.
So if all the epidemics were like this, with the high peak, then small seasonal peaks, we can say, okay, the war thing has passed. But it's not true. So the wars can be coming.
Yeah.
So it is important that this is captured by any model.
Yeah, and even we are working in this direction. Sorry.
No, the idea is that there is a competition between the viruses, and they are competing by the same population. So essentially, there is a kind of bias towards higher effectivity in all those things. So as soon as you introduce this kind of competition between them, you start to find these bigger and bigger peaks in the. More questions? No? I have one also regarding the seasonality, because it's you know that in the influenza list, this is a kind of polemic thing, no? So there are like different interpretations, including the one that says that it has to do with social interactions and blah, 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 no, that in summer and in winter, they are different or in more closed environments. And it seems that in your case with the antigenic drifting, it's enough. But I mean, for that to be really true, the antigenic drifting should have this kind of timing following of periodic of 1 year, 6 months.
Yeah,
Is that coming out like that? And I mean, just directly out of the network? Or
yeah, actually. So this is we are not making any trick here. We are just running the simulations with a constant set of parameters. And what we are observing is that here you have this season. The thing is that this seasonal behavior that is observed in data, that the concentration, you also have it in the evolutionary trajectories. You also have this kind of dependence. So basically, what I'm saying is that you are observing this without imposing the fact that you might have this yearly period. The only parameter you have to change is the antigenic, the typical length of until what point in the network you have immunity if you are infected by some variant, okay? And this is the free parameter you have here in order to play with the period. But if you adjust this parameter, you end up with an explanation which is plausible, okay? Without having to introduce this ad hoc.
Then you have to feed that one.
Yeah.
Okay. Any other question? No? Well, let's thank then the speaker again.
Gracias. Saludos a Alex de mi parte.
Vale.